for your lab submittals. So there were a number, like maybe 6, where there were issues with your lab submittals. So I fixed them all, but here's the issue. I think this is the problem. When you do a make hand in, it does a bunch of stuff. First, it does a make grade to make sure that's there. It makes sure stuff's not sitting in your directory uncommitted. It'll tell you about files that haven't been added that you should not add. Right? Give me an example of a file that we do not want in the repository. Py caches, good example. They're caches. So if make hand in complains, what should you do to get rid of it? Like remove the Py caches. They're just caches, who cares? So the other thing it does is it does a git push. It, in this order, it adds to a Google spreadsheet of mine. So this gives me some confirmation that you're actually running. So this uses if this then that. So just your name, the commit ID, and so on. So it pushes to Google spreadsheet, creates a tag, lab, whatever, hyphen or underscore submittal, one or the other. And then it pushes that tag to GitHub. What I found is like 5 of this. So one person just did never run make hand in. So I understand why nothing worked there. The other 5 people, or roughly the 5, what happened was it pushed, it added to the Google spreadsheet, and it never did the last 2. So here is my supposition as to what is happening. You're doing this, and it's asking you for your username and password for number 1 on the push, right? And then it adds to the Google spreadsheet. And then it asks for username and password again. It's like, why would I want to enter that again? Control C, okay? So if you're not going to set up SSH keys, which you should, you need to enter probably 3 or 4 times your username and password until it all kind of gets to the end and you're back at command prompt and everyone will be happy. At least I will be happy, okay? Because I had to go into the spreadsheet. Thank goodness I had the commit ID, find the commit ID, create a tag by hand, and so on. Make sense? So run make hand in until it gets to the bitter end. If you don't like typing your username and password, use SSH keys, because it makes your life better. Ryan?
Do you have a resource to guide me through setting up SSH keys?
Yeah, if you look at, I think it's lab 1, the very beginning instructions there is a pointer to SSH keys. Or just look at GitHub SSH keys, and it runs you through how to do it. And while you're doing SSH keys, set it up for Knuth too. So you can, I type SSH Knuth, right, those 10 characters, and it logs me in. I don't even type knuth.cs.hmc.edu, right? SSH Knuth, and you could do that with proper config settings and SSH keys. And you want to be lazy, but you want to be long-term lazy. And so long-term lazy means short-term you need to make a very, very small investment, okay, that will reap many rewards. And then once you've done this SSH key for the year, you'll be able to use it for other things in the future because you'll be used to it. All right, so we left off talking about virtual memory. We talked about the 0 page. And so these are some other optimizations we have. So these are, if you don't have the slides from last week, there are 2 copies you can all share somehow. So the idea here is a dynamic stack. Rather than allocating a fixed number of pages for your stack when you begin, allocate, maybe we can we get by with 0 pages? Let's say 1 page, okay? And then as your user program actually goes and tries to read or write from beyond the stack, so let's say here's the initial stack. So this is page 1 of the stack. So stack 1. Where will stack 2 be, Ryan? Below or actually, so if this is 0, and this is, max min, max int, where will the second stack page be? Below it or above it?
Would it be below it?
Yeah, because, yeah, stack pointer goes, the stack pointer decrements. So this will be stack number 2. But my idea is stack 1 is mapped, and stack page 2 is unmapped. And we have a lot of space between here down to 0. Okay. So what happens if we try and access stack page 2. Julius. What happens if I'm going to my, making some function calls, and I go into a function call, and all of a sudden I try and push a parameter on the stack in this page? I get a page fault. So what could I do? Map it. Yeah. Now, does that mean no matter what page fault I get from a user program, I should map it? Right? Allocate a page and map it? No. You know the address, right? You know it's like from the top of your, from the beginning of your stack down into here, and so you know how much space there is. So if it's in this range, allocate it. Make sense? So the advantage is using less physical memory because it depends on how much your program actually uses rather than how much it might use in the worst case. Questions on that? There's this question. Will the page fault, so let's see, Dave. Will a page fault necessarily be one page before the top of the stack?
No.
So could it be that I'm mapped here and this is unmapped and I don't hit stack 2 first, I hit stack 3? Is that what you're saying?
Yeah.
Because?
Because you could, I don't know, your stack pointer, you could just like put in a different value of your stack pointer, and then that would hop over that.
So I could do that by hand, writing assembly code or something. I could just move the stack pointer and do that. What C code, normal C code, could provide that?
Like allocating some sort of buffer.
All right, so like allocating a big, let's say, buffer. So I've got 10,000 bytes, which is bigger than one page. So I'm clearly going to go past this first page. When I write here, big at 2, is this writing, this is so difficult to say top of stack, because top of stack is down here, right? Is it writing lower in memory or higher in memory than big at 2,000?
Higher than big of 2,000.
Yeah. So think of it, our array is right, let's say here.
Oh, no, lower.
Right. So there's our array. This is the beginning address, so therefore 2 is here. So this is going to force us to go to another page. So what should we do, Gavin, in terms of what should we allocate? So let's say we write at big of 2, which is this page here.
Probably we want space. We want to either allocate just the page that was written to or allocate all that and all the pages in between that and the previous.
I would agree those are the choices. So either everything in between or one. Some of you I noticed on your homework allocated all the pages. So when you were doing the dynamic allocation of the S break, and there was no reason to do that. You just need to do the one they're using, because they'll never know if you don't map stuff that they never use. So I would tend to suggest just do the one stack page. Maybe you won't use these intervening ones, right? Maybe it's this giant array and you only hit one element in it, and when you return, it's going to pop back up over those pages. So, does that make sense? The disadvantage, of course, is if you knew you were doing this, you have to pay a separate page fault for each one. So, but make sense? All right. CopyOnWrite Fork. Right? We know fork copies all the pages. So what that means is when we have process A with physical pages, A and B and C, when we do a fork, we now have A and B and C, and A prime and B prime and C prime, which are duplicates, right? And so now we've got process B, or process, let's call it. If I'd thought more, I wouldn't use the same letters for these. But basically, the page directory is pointing at A prime, B prime, and C prime, right? And that's not necessarily bad. If you want to do a fork and have two processes running along and they are manipulating their own memory, it's okay to have them be separate. The problem is, Gabriel, what often happens after a fork? What system call? Yeah, one of the execs, right? One of the many in the exec family. And so what will happen to all the pages in a process when you exec a new process? Gets rid of them all. It just gets rid of them all and reallocates. So it seems very wasteful to go through, carefully copy every page, and then 99 times out of 100, throw them away. So the solution is we will instead, so we won't do this. Let's see if how to describe this or write this. So here's what we'll do. In process A, let's actually show our page table. So here's our page table, right? And it points to A and B and C, not necessarily in that order, but, right? And what we will do for process B is create its own page table. And we'll reference the same A and the same B and the same C. If they're all just reading, this is fine. You and I can both read the same page, and as long as no one writes it, we won't even know we're sharing it. But if someone writes it, that's a problem, right? If I'm a process that's forked from you, if you write a page, that's a problem because I can see it, and I shouldn't be able to see it. So if you're going to try and write the page, then we should have a page fault and make you make a separate page then. So instead of duplicating all the pages ahead of time, duplicate them on demand. So if we're going to do that, what do we need to do to these page table entries to ensure we're going to get a page fault if process A tries to write to them? Right on.
Well, we should be marking them so that they're copy and write.
So, yeah, okay. The processor has no idea of copy on write. So what are we going to do for the processor, the MMU, to get what we want?
So we would want to modify our PageFault handler in the kernel so that it checks the...
Back up.
Yep.
That assumes we're getting a page fault.
Oh.
What are we going to do to force a page fault?
Oh, we can mark the page to be not present.
Yes, so we need to, no, well, that's a bit much. Because if someone tries to read it, fine, read all you want. So we'll mark all these. Not writable. And same thing here. Okay, so if they're not writable, we're going to get a page fault on a write. Now we can go through, we have to have our page fault handler know what to do. It has to know these are copy on write. So this is very similar, the copy on write, to what we saw in the 0 page, where stuff that's initialized to 0, we provide one single 0 page. And then if anyone ever tries to write to it, we give them their own 0 page. So it'd be neat if the, yeah.
So if no writing happens, then A prime, B prime, C prime.
Yeah. So these guys are no longer there, right? We never made A prime and B prime and C prime. We only make them on demand. Okay. And we can't just do this in the child process, right? We've got to do this in both processes because either one of them might write. So then what we've got to go through is somehow we got to keep track. We want to do a copy on write. We could use a bit in here, right? Remember there are 3 available bits. So we could designate one of them as copy on write. And that could be our hint to make the page fault handler quicker. It could just go to the page table entry, see, oh, copy on write. Go ahead. Okay. Drew.
So if process A tries to write to the physical page after the fork, it would have to create its own copy of the physical pages now?
So the parent,
Yes.
I'm just repeating your question. So if after the fork, the parent tries to write to one of its pages, then it would have to create a duplicate. Yes? Okay.
If the child does
Why?
another fork, will all of those have their permissions changed? Like, will all of it's like A, B, C, D, and A prime B? Like, all the page table entries that correspond to those have their permissions set for the before the fork? Or just so like assume like process B actually does some editing.
Okay, so process B does some editing, so we now have, let's say, an A prime here.
Yeah, and that
Basically,
would be marked, like,
yeah.
writable, right?
Basically what we'll do is mark these all as copy on write, make them all not writable, and then duplicate the page table.
Okay.
So we're going to end up with a different page table from up here.
Right. right? So whenever a fork is done, it will first like mark the pages accordingly first before like doing the like.
Yeah, it's got to do it before that other process gets a chance to run. Really, you had a question?
Yeah, so let's say process A writes to physical page A, so you make a copy. Then if process B wants to write to physical page A, then does it also make a copy? So then do you have three copies for only two processes?
So unless you have some external data structure, then yeah. Ideally, let me give you an example. Let's say this guy does an exec, right? He frees all these pages. Actually, no, let me back up a second. We can do it with the information we have today. Because the other thing we can do here is when we make a new page table entry that points to this page, it's actually pretty critical that we increment the ref count in the page info, right? Because we want to make sure that if we free up this page table entry that points to this page, that we don't free up this page if another process is using it. So our ref count will tell us how many processes are, roughly here, how many processes are using it. So that'll make sure it doesn't go away. The copy on write can look and see if the ref count is 1, no one else is around anymore. And so therefore, we don't have to copy it. We could just set it back to writable. Okay, so, but you can see it requires some extra data structure besides the page table entries because it's shared among different page tables in different processes. And the ref count gives us exactly that. Other questions? Yeah.
So, but if the child is long running, then that doesn't really seem to solve the problem because you'll still have the child having a reference to the pages. Meanwhile, the parent is modifying its pages. The child is has been exec, so it's doing its own thing. But
once the child is exec, all of these are going to get decremented.
okay.
And so therefore we'll be okay.
Usually it'll just happen immediately.
Yeah, usually it'll happen immediately. Yeah. This is one of, so Project Lab 7 is a design your own adventure. And so this is one thing that you can do, for example. We do have a default one, if you don't want. Okay. Did you have, okay. Next one, exec, right? Exec loads your entire executable into physical memory. A lot of times, not all the pages are used. I'll give you an example. I run Excel. Excel has 10,500 features, and I use 3 of them. Okay? So all that code is wasted in memory if it's in physical memory. It's wasted on disk, too, but there's nothing I can do about that. So the idea is we have this wasted pages, and it also takes forever to start. Right? It certainly would if it actually loaded all that memory. So the idea is exec should mark, it knows the range of where the code is, right? In virtual space. And so it should mark it all as not there, not present. And then have our PageFault handler that gets yet another task is, if you're in the stack, go allocate a page. If you're CopyOnWrite, go allocate and copy the page. And now, if you're in the code space, go load it. You obviously can't return a 0 page. Where do you get the code? Where do you get the data in that page from? TY.
Can you repeat the?
Yeah. So you get a PageFault.
Yeah.
You know there's some code right in here. I need some code here. Where do you get it from?
The here is like where you got
The here is in memory. So I am at virtual address 7526334. That page, where should the memory come from? That is, where should the contents? I can go allocate a page. What am I going to fill it in with?
Isn't that based on like the code itself that you're like trying to run?
Okay, yes. Well, it is the code I'm trying to run. Where is that code if it's not in memory?
So it is not in memory?
It's not in memory because we didn't load it.
Oh, right.
So if we were going to load it originally, where would we have loaded it from? Right, when we do an exec,
Yeah.
we want to load all the code. Where do we get it?
From like the code.
The code segment, in our ELF, right, in our executable. So where are we going to read it? Where are we going to read a single frame from, a single page from?
Do you not still go to the same code segment?
Yep, you need to go to the same code. You're going to just be going over and over again now, right? Originally, you just did one big read. Now you're going to go and get one on demand. Yep. So you're going to have to keep that open, right? I'll give you a good example why you have to keep it open. Because if you close it and then go open it on demand, like what if I just got sick and tired of Excel and I deleted it while it's still running? It would be bad for it to just blow up. It'd be nicer if it kept running. And that's, with Unix, kind of works. Because if you delete a file and someone has it open, it's still there. This is one of the nice reasons why that's nice. Okay, so on the PageFault, we read the corresponding disk, install the PTE. What if the file is larger than physical memory? Oh, get a question.
Well, so if you delete it, then I get how that would work. But what if someone else just goes and recompiles it or modifies it in some way while it's running? Like, I feel like you don't...
I was actually thinking about this as I wrote this. It's like, yeah, you're out of luck. Okay. So the good news is I don't even have the source to Excel, so I can't compile it on the fly. But if I catted garbage into it, that would be a problem.
Does that actually like mess things up on Linux? Did you try that?
I am 95% sure your executing program would then just fail as it tried to page in this new stuff. So, what if the file is larger than physical memory? That is, well, without demand paging, we just won't run, right? We'll say you can't, exec will fail because there's not enough memory to load it. Here, though, we should work, right? In the Excel case, if I'm only using 1% of all the code pages, then only those 1% will get loaded in. Does that make sense? Okay. Now the question comes about, fine, I'm using Excel, but here's the way I use Excel now. I got a book on Excel and I read through, and now I understand 9,000 of the functions that you can use, the features. So I'm going to go, in fact, I'm just going through the book, page by page, right? Feature by feature. So I do feature 1 and feature 2 and feature 3 and all the way to feature 9,000. All right? So it keeps loading more and more code pages in. But it turns out I never go back to feature 1. It's like a lot of learning. You know, it comes in one ear, I do the thing, and then it goes out the other. Okay? So the page 1 code, I actually never need again. The feature 1. And the feature 2 code I never need, and the feature 3 code I never need. So theoretically, even though I have a small amount of physical memory, right? So here's my physical memory. And here's all my code. And I will eventually go through all of it. I never need it all in memory at once. And so that's the idea of virtual memory. So not all of your process's address space needs to be in memory at once. And this works reasonably well because of the 90-10 rule, right? Processes spend 90% of their time in 10% of their code, kind of roughly. So I just keep the pages I'm currently using in physical memory and let the operating system throw out ones that aren't being used and pull in other ones that are being used. So we get this illusion of near infinite memory, right? It looks like we have the entire address space available to us. We can fit more processes in memory because each process is using less physical memory, so there's more physical memory to go around. And the reason this works is due to locality. So we have the spatial locality that if I'm using something in this area, that it's likely, I'm more likely to use stuff near that than other places. Makes sense in code, right? If I'm executing this instruction, it's pretty likely I might be at the next instruction. Right? Or even if not, maybe I'm branching back to, in a loop, going back, and still in the same page or +1 or -1. For arrays, the same thing is true. Often, you access an array sequentially. And so therefore we have the spatial locality. And then temporal, the likelihood of accessing a resource. Let's put some more words there that I believe got chopped off. So what might be good here? Gary, what would temporal locality be?
It would just be like things that were accessed like recently.
Yeah, the likelihood of accessing a resource is higher if the resource was accessed recently. Right? And one way to think of this is that your disk is a cache for your main memory. Let's look at it the other way around, in fact. That would be a poor way to do things. Yes, your memory is a cache for your slow physical disk. Yeah. As soon as you implemented that, you'd find out that it wasn't working very well. So what does your PageFault handler need to do now? It's more complicated, right? You need to figure out the virtual address, of course. If it's a protection problem, signal or kill the process, as we're doing. If we don't have any free pages, right, physical pages, then we need to free one. How do we do that? Well, we got to keep somehow some sort of a master list of our pages, which we actually have in page info. And we need to keep track, has this page been modified? Right? If it hasn't been modified, then there's no reason to save it, because we can always just recreate it however we got it in the first place. Otherwise, we need to write it to some place on disk. And remember where that is, because later on we'll need to get it. And then we need to suspend the faulting process, because this write is going to take a long, long time. Right? If we're talking about a disk, this might be 10 milliseconds, let's say. How many instructions can you do in 10 milliseconds? A lot is yes. That's qualitatively correct. At least 12. Yes. So if we look at a gigahertz, right? Gigahertz processor. So how many nanoseconds are there in a
about a million
gigahertz?
in a millisecond, about 10 million in 10 milliseconds, I think.
Yeah, about 10 million. So 10 million instructions, you can get a fair amount of work done, right? You could probably, yeah, anyway, you could do a lot. So therefore, we don't want to just wait. We'll, in fact, talk about that with interrupts later today. So instead, just the current process that wants a new page, it's going to have to wait, okay? 10 million instructions. So we put it to sleep and we go do something else useful. Once that write has completed, if it was necessary, then we can continue on. Because now we can capture that free page. And now we have to figure out where we're going to fill it from. Maybe it was previously saved to the backing store. Maybe this is from our executable. Maybe this is one of these fill on zero pages. And in any case, we then go ahead and fill it appropriately.
So when you put that process to wait, kind of like some arbitrary number that like the operating system, like how long?
To sleep.
Yeah, to sleep. Like how long does it sleep?
Till it's woken up.
And it's waking up when
In this case, when the read completes, the write completes,
okay.
it'll cause us to wake up.
Okay.
We suspend the faulting process unless we're filling with zero. Right? If we're filling with zero, we can do that very quickly. But otherwise, backing store executable means we're reading again, and that's slow. So we'll suspend the process again. Update the page table, restart the failing instruction. That's virtual memory.
That sounds really slow.
It is.
Is a backing store disk or memory?
It's disk. Because you've had memory, you just use memory, probably. So it could be an SSD. It could be a dedicated disk. It could be a file on disk. One thing you need to be careful of, for instance, I don't know what Linux does, but on Mac OS, that is a file, and it's encrypted. Why is it encrypted? exactly, because there might be keys and stuff inside it.
So we write the evicted disk into, the evicted page into disk, and then after that we have to load whatever new page, possibly from disk too, right?
Yes, from disk if it was
Yeah.
previously saved,
Yeah.
or from your executable.
Okay.
So, other questions? All right.
What if you run out of disk space to store it to write to the backing store?
That's a problem. So if you run out of disk space, it's bad. So you could kind of wait around hoping that some program will kind of finish and doesn't need any more pages. Or kill a process, maybe this process, maybe some other process. So, but there's not a lot you can do. Memory map files. This is a feature that page tables can provide us. So normally we use open, close, read, write, seek. We have a system call interface in order to manipulate files. The idea is you take a file and you map it in your address space. So let's say in my address space, I have foo.txt. Right? It's a big text file that goes from this virtual address to this virtual address. And so if I want to go modify the 10th byte of it, I start at this address and I say @10 equals whatever I want the byte to be. So the kernel is reading and writing to the file, not live, not when I actually gotta go change the 10th byte of it, but instead when this page gets unmapped. Let me back up a second. That's not quite true. When this page is no longer going to be in memory. So let's say this page was chosen to be written. Well, we wouldn't write this to the backing store. Where would we write this page? Right here. We'd write this page to foo.txt as the first block. So you can read and write using these memory accesses, and then this data is cached in here and eventually makes it to the file.
Would we
Sarah.
ever move this out of memory before we need another page immediately? Could you have something that goes around and moves dirty pages out of memory?
So yeah, this is, yes. So you would definitely, there's a lot more, and we'll talk about VM in more detail later, but it's a good idea. And the idea is, right, it's slow to wait for a free page. And so it's better to prophylactically, or that's not quite the right word, but that'll work, go ahead and take dirty pages and write them out. Right? So just go through and write out dirty pages to your backing store or to their file, just in case someone needs pages in the future, if you've got nothing better to do. Does that explain that? That was
If it was never modified, do we have to write?
Yeah, that's a great idea. If you never wrote it to it, then there's no reason to write it back out. And that's where we can use the dirty bit in the page table. So the hardware does support that.
What if someone else opens foo with normal file system calls and then either starts reading from things that have been modified in the memory map but haven't been written out yet, or starts writing to it?
There has to be a coordination in the kernel between the file system work and this memory mapped I/O, such that basically there's a cache of disk buffers, and it has to make sure that this page is being used not only here for the memory mapped, but also used as the cache for reading from the file. And it's difficult to change the end of file here, because it's not clear what you do. You have to have some sort of a call to say make it smaller, make it bigger. Oh, what else can you do? You could do distributed shared memory. This is doing this again. All right, distributed shared memory. So you could have, let's say, 3 different machines on a network, and you can have address space. This address space is actually memory from machine A. This is from machine B. This is from machine C. And so if anyone wants to do a read or write from machine A to this address space, we're going to actually do some communication to B and back.
Sounds really slow.
Can be slow, yes. But if you have very fast networking, it can be faster, for instance, than reading and writing a disk, for sure. So. Page sizes. Smaller page sizes, less internal fragmentation. Because remember, if we have a page, let's say here, actually, let me not use this. Let me use foo.txt. How much internal fragmentation does this memory mapped foo.txt have? At most, at least, on average. Ishan, at most. I'll say a full page minus 1, right? Because if it was a full page, we wouldn't have allocated it. And the least, and the average, half. Yeah, so on average, we have a page. So smaller pages means smaller, less internal fragmentation. Larger pages, every page table entry covers more bytes. Smaller page, let's put in the word table here. Right, so our page table is smaller. TLB we have not covered. And we're going to cover that later. But the TLB is just another cache. It caches frame numbers to page numbers. Okay, so it's basically going through the page table. The end result of it is cached. And that's important because otherwise every memory access of a virtual address actually takes 3 physical addresses. The first level page table, and then we got to go to the second level page table, and then we get the actual address. And so slowing down your memory by a factor of 3 is considered bad form. Okay? So we have the TLB, which is this, the cache, basically. So translation, look-aside buffer. And it's a cache of virtual page number to the associated page table entry. Because you want to have the flags too. You want to know whether it's readable or writable. Yeah, Ishan?
The hardware knows that you have like a 2-level page table. So you can't exactly just change it to something else.
It knows you have a 2-level page table, and yeah, you couldn't change it to something else. That's correct. Okay. That's not 100% true. So x86 knows it's a 2-level page table. The RISC-V, right, which is a new open source, the right word, open licensed architecture for RISC devices, has different settings that you can use. So actually, even if we look at the x86, the default is 4096 for your page size, but you can actually do 4 megabytes. By the way, this is, what is this KIB? Does anyone know? Kibibytes. Yeah, kibibytes meaning a kilo base 2 rather than base 10. So 1024 really, and not 1000. So these are mebibytes. Mebibytes. I believe it's correct. Anyway, the RISC-V, you can have up to like 512 gigabyte pages. I think they're being forward-looking.
Is that just using like 1 page for your entire memory space?
Well, no, because they'll do 64K address spaces. So there's a lot left. There's a lot of pages you can still have. All right. Thrashing. So thrashing, let me quit and go back in here. Thrashing is when you're doing more time paging than doing real work. Okay? So I go, someone wants a page, there's lots of pressure on memory, right? And so I kick someone out, and then I pull a page in, and then when that guy comes in, well, he needs that page. And so he goes and asks for another page, and we're spending tons of time paging to disk. The old style hard drives with the lights, it's just going, ooh, and like nothing's happening much on your machine. So the problem is if you have too many programs running, right, it sounds fancier to say the degree of multi-programming is high, but we have a lot of programs running. Each process's working set is not resident. So the working set is what are the pages it actually needs, kind of right now and for the next little while. So if it had those, it wouldn't be asking for more. Well, if you can't fit your working set in memory, it's going to be asking for pages. And so if there are too many programs, all of which have their working set too small, you're going to get this thrashing. So the solution is kill some programs, right? But there are a variety of ways you could do it. You could kill it. You could just take the entire program and shove it out to disk. Say, we're not going to run you for a while, right? And leave all that physical pages for other programs. That's called swapping. Put it on a timeout, that's right, with some other friends too. But they can't talk to each other, they have to be silent. And then when we see that the thrashing has stopped, we can start pulling processes back in. All right, the JOS virtual memory layout. This is just a useful, nice looking diagram here. So some things to note, and this is going to be relevant soonish. We have multiple CPUs we support, and each one has its own kernel stack. So we don't have a stack per process. We have environments, right? Environments are kind of like processes. They're like lightweight processes. And so those are available to be read by the user. Okay, because unlike POSIX, Unix, XV6, we're going to allow our user processes to have a lot more insight into what's going on and a lot of control. So it can actually know about page tables and things like that. Yeah, that's all I want to show there. All right. Now we're going to talk about interrupts, exceptions, and we'll talk again about system calls, although we talked a fair amount about that. But there are interrupts, exceptions, and system calls all use the same mechanism. So I would say this is a common theme for interrupts and exceptions. System calls is not quite true. But the idea is the hardware wants some attention, okay? And it wants it now. And so we need to do something. Why does it want it now? Well, it's trying to translate an address, a virtual address to a physical address, and it doesn't know how. Give me a name for that. David? Yeah, so when the memory management unit can't convert a virtual address to a physical address, what's the name for that? Kind of an exception. Yeah, that's PageFault, right. Divide by zero is another example. Users trying to execute some privileged instruction that's not allowed to, like set the CR3 register or do an interrupt, not 40, but some other kind. Like let's say it's trying to do a PageFault exception interrupt. We don't want the user to be able to do that. Network hardware and delivered packet, yeah.
So if we're really just using paging rather than segmentation, then why do I always get segmentation faults when I write C instead of page faults?
Because we have this idea of segments. So it's not segmented hardware, but we have segments, our code segment, our text segment, and so on. And so that's where the naming is coming from. Hardware, right, in general, some I/O hardware wants to deliver some information. The timer wants to tell us tick, tick, every so often. If you want to, CPU 1 might want to tell CPU 0, hey, flush your TLB. All right, and so that would again be an interrupt. So those are some examples. 3 basic flavors: exceptions, system calls, and interrupt. And this is more sort of the Unix terminology as opposed to, let's say, x86, where they talk about just in general interrupts. But exceptions, what happens? So an exception, a fault is a kind of an exception that might be fixable. So in that case, the saved instruction pointer is the instruction that caused the problem. So on a page fault, right, if we're trying to write to memory and we fix the page fault in a kernel, we want to go back and try and write to memory again. Okay. And so therefore, we don't want our instruction pointer to be the next instruction. We want it to stay at the same instruction. There are aborts that are not fixable, and there it's like often not even documented what the EIP is. Okay? An example might be a double fault. You fault while you're handling a fault. Okay? Or a triple fault, you don't even get an exception, it restarts the machine. System calls, these are intended exceptions, right? So it's an exception that the user program is making to communicate with the kernel, and there the instruction pointer is after the interrupt instruction, which we know. And then for interrupts, this is some device wants attention, the instruction pointer is the next instruction to execute. Okay. So where do interrupts come from? The interrupt, right, is a signal to the kernel that some hardware wants some attention. And there's a driver in the kernel that is responsible for dealing with that hardware. That's just how stuff is normally written. You have a device driver. Right, so this is AKA device driver. And in many cases, the number of lines of code in a kernel is mostly device drivers. Okay? And unfortunately, scarily, sometimes the device drivers are written by manufacturers who don't exactly know what they're doing always, and so that's why sometimes device drivers are some of your buggier kernel code. Windows NT tried to fix this by having the device drivers outside of the kernel, but unfortunately that caused performance problems, so it moved back inside the kernel. So here's what happens. This is on x86. We've got a local APIC, Advanced Programmable Interrupt Controller, for each of our cores. Okay? It used to be that was a separate physical chip, but it's now integrated into the x86. So every core has one of these APICs, and it will provide an interrupt to this particular core. So you can have local interrupts coming in here, like let's say from the MMU, and that might go to that particular core, right? Because this core was trying to write to a particular memory address. These LAPICs talk to each other over the system bus, and then there's an I/O APIC that is responsible for the I/O devices. So the I/O APIC will then cause an interrupt that goes through to the local APIC, and then that will cause that CPU to interrupt. And there's a separate thing that happens for PCI, and there's this is sort of legacy now. I mean, it's still used, but most stuff for the future just uses a system bus, so that devices can just talk directly to the system bus and provide interrupt information. Okay. So what normally happens is an interrupt comes in, and we know that that gets routed through a table to a particular vector, and that's called often the interrupt service routine, the thing that deals with the interrupt. It might do a lot of work. It might do just a little work, just kind of note what's happened and schedule something to be run later. Theoretically, you can do I/O without interrupts. Right? You can just keep asking a device, hey, do you have anything for me? Do you have anything for me? For a keyboard, let's say. And that's polling, but that can be slow. So let's say we don't have interrupts and we're trying to do I/O. We've got some code, and then there's a write, and some more code, and another write, and some more code, where the code is 1, 2, and 3. And so we do our first write, and it goes in the kernel, and it does some pre-write stuff, some setup stuff. And then it actually makes a command to the device and says, write this. And then it's got some stuff it does after the write. Part of what it has to do is just wait for the device to say it's done. Right? So after 5 happens, then we return back, and the write is finished. And then we go on, and we do the next one. And we do this write, we go, And we know when it returns, the write is done. Okay? The write has completed to the device. The problem is, this time could be expensive, right? If we're writing to a hard drive, we decided that could be millions of instructions. And so the kernel is not going to waste those millions of instructions, so it's going to suspend our process, right? Put it to sleep, and run some other process, or many, many, many processes with those millions of instructions. Well, maybe this code, let's say there may be 990,000 instructions right here that it could very well use if it could. And so it'd rather use those instructions on its behalf rather than someone else's. So in the interrupt case, it looks slightly different. We run our user code. We do a write. The write says, OK, let's do the pre-write stuff, and let's issue the actual write to the device. And then let's just return. Okay. So we return to the user code. And part of this pre-write is going to say, hey, when you're done, let me know. Okay? So, you know, you hired a gardener to go dig a bunch of flower beds, and you just say, give me a call when you text me once you finish, as opposed to sitting there and watching him. So we're in the user code, and then eventually, this device is going to say, hey, I'm done. That's an interrupt. What happens? Interrupts cause us to go into the kernel, into our interrupt service routine. And it's going to go and figure out what device it is and on whose behalf and what happened. And eventually, it's going to go execute this post. Whatever we need it to do here, it'll do here. Right? It won't have to do that polling here, but whatever it might need to do. And then we'll return. Where do we return? Where we left off. One of our 990,000 instructions in here. So we don't even notice it happened. Right? It's just there seemed to be a suspicious gap between this instruction and the time the next instruction ran. And then if we do a write again, the same thing happens. We get an interrupt. Dave?
So this is just review, but like, where is this user program code stored in? That's in the code segment?
That's in the code segment, yeah. So this is somewhere in the user address space. Yeah. Okay. True.
So I'm trying to understand, if you have the IO command, and from there if it comes back to the user program, it can't do anything in the user program space until the IO command completes, because maybe the next instruction has a dependency on the completion of the write. So I'm trying to understand why return if you can't.
Yeah, so that's a good question. Let's differentiate reading from writing. So if we were reading, we can't safely come back until the read is completed, because the next instruction, you're right, might start reading that data. But if we're writing, all we really need to do is make sure to copy that data out of user space somewhere in the kernel. Once we've copied it out, we can write it at our leisure. Does that distinction make sense? That's a good question about the reading, because you're right, wouldn't work for read. Other questions? How does the interrupt actually work? I mean, as far as how did they implement it? It's really fairly simple. We've got this fetch, decode, execute cycle, right, that the CPU goes through. Fetch an instruction, decode it, execute it. At the beginning of that loop, it checks and sees, basically, is the interrupt line on? Line or lines. But basically, they're just lines coming to the CPU. Is it on? If it's on, I won't do this. I will go do my interrupt. And when I complete with it, then I'll do it. So it just pauses the fetch, decode, execute cycle.
There are multiple interrupt lines coming into a CPU. How does it know which one?
There are priorities. So they're either sort of hard-coded priorities. That is one way things are done. So you have interrupts levels maybe 0 through 7. And we say that lower interrupts are of higher priority than higher interrupts. And so depending on the device, it has a particular level.
So you said that interrupts didn't involve any polling, because if it was me, we could do polling on device drivers. But it seems that this is polling. Yes.
This is polling, but it's not us having the software do polling. So this is the hardware doing polling, yes, at every single instruction, but very quickly.
Okay.
Yeah, that is true. It is.
Polls the late bit, right?
Pardon me?
Does it poll late bit?
Yeah, it's yes, yes.
In the XV6, like in the trap function that we've been working with for the homework, after each of the cases, there's some call to some LaPick function. What does that do?
I think I would have to look at it to remind myself, but I think that's acknowledging the interrupt. Basically to say, okay, you can turn it off now, I dealt with it. Because it could be a device interrupt, and another device comes in at a higher priority, so it's not going to necessarily get handled at the next instruction. And there is a question that comes up. You asked about priority. So the other way is programmatic priority. So you can actually control which interrupts are at what priority. And then the other question is, what happens if you have a lower priority interrupt executing and a higher priority interrupt interrupts? Can that actually interrupt the interrupt routine? And that's up to your kernel to decide. So if there's an interrupt pending, basically at the beginning, the CPU, suspend execution of the current program, save context. It's just like a trap, right? Set PC to the start of the interrupt service routine, ISR, via the IDT, which is our interrupt, I think it's interrupt descriptor table. Just a well-known location in memory, because we've got a register that points to it, that has, where to go for what interrupt. So this table is not the interrupt service routine. This table is a vector to the interrupt service routine. Or could be separate service routines. In our case, we have one called in XV6, trap. We process the interrupt. That is, we execute the interrupt service routine. And then when that interrupt service routine finishes, it should do an IRET, return from interrupt. And then we go back to either the same instruction or the next instruction. Questions? Ashley?
So when the write is happening to disk, does the CPU continuously have to do that? So like, does it just send it to a different CPU, or like how does we have to wait for it to finish? But then the CPU keeps going. That's what the interrupt is for. But the actual writing to disk, and like while we're waiting for it, what is doing that?
So that's a good question. Let me just move ahead. So here we go. Let's say we're a dumb device. So we're trying to read instead of write, but same idea. Okay, so we're trying to read in this address. We tell the I/O device to do a read. We say, here is an address. You write here. Okay? And maybe it only writes 8 bytes, because that's the kind of stupid device it is. And then after it's written that, we increment the address and we say, okay, now write this one. And then increment, okay, write that one, or so on. Okay? But in any case, we are telling our device to do that. We wait for an interrupt to be generated. I lied there for a second. We don't actually give it the address. Instead, we say, give me 8 bytes. Okay? Which we may be using an I/O instruction or memory mapped I/O. And so we're just getting some bytes. And then we write them into XXX. And we might even have to loop doing that. Okay? DMA, which stands for Direct Memory Access, says instead, hey, device, you're a smart device. Let me give you the address to write to. And you go do that and don't bother me until you're done. Okay? So the device is actually going to be communicating with the memory bus. If the device is communicating with the memory bus, that means we have to provide it a physical address. Which means we have to make sure not to move it in the meantime. Which means we need to somehow keep track of that and lock it and note that. And what happens then is the CPU is trying to access memory. right? And devices may also be accessing memory. So it can be stealing cycles for us, because we're not using it all the time. There are times when we're working from registers and stuff like that. So it sneaks in and does some writing and sneaks back out. But that's direct memory access. All right. How do we know which device interrupted? We can look at the trap number. Okay, so timer has one, serial would have one, other things. The interrupt descriptor table has an instruction, really a pointer, a vector to go to with each vector number. For us, in XV6, we jump to all traps. Okay? It's more convenient to have a single routine than 30 separate routines. And so therefore, we need to push the vector number first, which is basically the trap number. Okay? And we've seen this. We saw this with system calls. So, right, we have our IDT register that points to the interrupt descriptor table, and each one of these has basically where it's going along with the segment selector. We don't use the segments, right? We just basically, these are linear addresses. Again, this is like we already saw with traps. XV6 will write to our LAPIC. The timer is actually integrated with the LAPIC these days. And so we can tell it we want to be periodically called. We have TV init that initializes our segment, so it basically sets in the interrupt descriptor table in a particular entry the segment, which we're not using much, but we have to have a segment, and where we want to go. Two things to note. 0 versus DPL user. DPL user is what number, Sarah? Or what is the protection level for user code?
3.
3. So for most of the interrupts, we say you have to be in, you can't generate this directly from user code. Okay, the hardware can generate it, device can generate it, but you don't just get to say interrupt 16. Okay, user code's not allowed to do that. But one interrupt, it should be able to do that for, and that is interrupt 40, which is our system call. So for the system call, we say, yeah, user can do that, because we need to give them some way to get into the kernel. And this says, do we want to allow other interrupts while this interrupt is being handled? XV6 says no. The only place we're going to allow other interrupts is during a system call. But any other interrupts, it has to complete before a new interrupt can come in.
What's the seg K code?
The seg K code is just you have to have a segment descriptor, and so we have a segment descriptor that we use for kernel code. So it's not 0. There's a segment, a table of segment descriptors, and the first one is empty, and that's 0. So it's 1 or 2 or 3, something like that. Okay? And it's just set up with linear addresses, so it hardly, it's not doing much of a segment mapping at all. What stack do we use for an interrupt? If we tried to use the user stack, we could have some big problems. Does anyone require that? Could you run a user program and use the stack pointer as just another scratch register if you wanted? If you didn't need a stack? Yes, no one forces you to say that points to some memory that you're allowed to write to and so on. It doesn't have to contain an address. So not good to try and use the user stack pointer. So instead, we can configure for each CPU what stack pointer it's going to use. Okay? And in JOS, we're going to have one stack pointer for every CPU. And in XV6, we have one kernel stack for every process. So when we create a process, we create a stack for it, one page. So as we're switching user processes, we switch stacks, along with switching page directories. I don't know if it matters that much right now, but there is a scheduler running for every single CPU. So every single CPU is cycling through the list of processes and figuring out which one can be run. You know, which one is ready to be run and running it. Nested interrupts, I'm going to ignore that a moment. And I want to talk about your homework, which, by the way, is graded. You say, how is that possible? Well, I was just working before you got here. So we have to deal with interrupts and system calls. If only your lab was as easy to grade. So I am in the midst of that. So we got this alarm test, right? This is what was given out. We want to call this routine, periodic, every 10 ticks. And so therefore, we should have interleaved sort of writing these dots and writing alarm. And your job was to implement the alarm. So what do you need? You need a system call. You need to count the ticks, which means you need a timer interrupt. And you need to call back. New system call? You guys have done system calls already. No big deal, right? Counting the ticks? Not so bad, I don't think. So we have, actually, let's look at the system call first, right? We do need to read the ticks. And let's go ahead and sanity check it. Make sure it's not less than 0. We need to take the handler they give us. So this is a arg pointer checks to make sure it's a pointer into our space, which is good because a sneaky user would try and cause a handler to be run in the kernel. And that'd be bad. And so we just save that, right? So we've got this thing to call. The way I did it was the number of ticks left until calling. So I think this one counts down is the way I did it, but you could count up, it doesn't matter. And then we already have our timer, right? So this means the timer is going off. So if our timer is going off, we want to increment. Maybe. We need to make sure we have a process running. And we need to make sure that we're in kernel mode. Sorry, in user mode. Why do we even need this check? How could we not be in user mode? I'll leave that. We'll think about that. OK, so I'm just saying it's important. And then if our count is greater than 0, we decrement the count. And if we got to 0, it's gone off. Right? So that part's not hard. The problem. So let me give you one possible way you could write this. And in fact, people wrote it this way. OK, it's gone off. Let's just call the handler. What happens? Does it go to the right instruction? Does it actually get to the periodic function? Well, this is a user address. And our page table now includes the user, because it's this process's page table. So it'll go there. And it'll start executing periodic. What's the problem with that, Sarah?
I mean, we're still in kernel mode.
We're still in kernel mode, and we're executing user instructions. This is a bad security hole, right? We've got another problem. Let's see. Let me remind myself what this problem was. Oh, right. So here's what happens. We're going to get into our write system call. Okay? And it'll do fine all the way up to there. And then when we get in the system call, it's going to want to do a fetch int. Okay? Fetch int uses the traps frames ESP. But remember, the hardware, there's a couple of values that it won't push on the stack if you're going from kernel to kernel mode, only if you're switching modes. And in this case, we're still in kernel mode when we execute the trap, right? So this is our trap, our interrupt. And since we're going from kernel to kernel mode, it doesn't push the ESP. And so therefore, when we go to try and read and use the ESP, what's its value? Whatever happens to be there. And so when we try and access that, we had a problem. Okay. But it's scary how close it comes to working. And the motto is, you are provided a series of features that if you carefully work together, you can provide protection. But it's not at all automatic.
You said the problem is that the stack pointers point in the wrong place.
It's not that the stack pointer is pointing in the wrong place. So, right, when we do an interrupt, it saves a bunch of registers, right? Saves registers. Saves some registers. One of the registers, ESP, it maybe saves. It will save if we're going from user mode to kernel mode, but it won't save otherwise. And so therefore, it's not saved. We've got this structure defining our trap frame. We assume that that stack pointer points to our user stack, and it doesn't. It's whatever happens to be there in memory. So that's the problem. So it's not like the stack pointer itself got messed up. It's what we thought was the saved stack pointer is not the saved stack pointer. It's random garbage. By the way, one other problem is whose stack are we running on? Say it again? Yeah, the kernels. That's only one page big. If we've got a recursive periodic routine or something allocates a big buffer, we're blowing away kernel stack. So all bad stuff. So here's number 2. So we just go through and are tricky now. We do not call the alarm handler from the kernel. Instead, we say when we return from our interrupt, then the code that we want to execute is the alarm handler. Well, when we return from interrupt, what code gets executed? Whatever's in the EIP of the trap frame that we were storing. So we change the EIP to say return to the alarm handler. And that works up to a point. Okay? Indika, up to what point does it work? Does it print? It prints alarm. And then it has a very odd behavior, doesn't it? What's the odd behavior?
It returns to the top of the main function.
When periodic returns, it returns back to the beginning of main and starts executing from the beginning of main again. And so you have an infinite loop of main, periodic, main, periodic, main, periodic, and on and on and on and on. Right? Yeah. So here's the problem. Where should periodic return to? Who even called it? Was there ever a call to periodic? No, there was just an interrupt return into periodic. Where do we want it to go? What's the original? Where in alarm test? As long as we change the word after, I totally agree with you. So the next instruction after the one that, where we had the interrupt for the timer. So that's where we want to go. But How are we going to cause that to happen? Well, set up your stack so the right thing will happen, right? So if your stack is here, and we've got the address of the alarm handler, so the address of periodic on the top of stack. So in this case, let's see, 0 is up here. Sorry. Yes, so top of stack is most negative. So 0 is up here. So we've got periodic here, and what we like to do is when periodic returns, we go back to where we were in the alarm. So when periodic returns, it's going to be looking for a return address here, right, on the stack? Because it'll do a return, and it'll pop up what's on the stack and go there. So if we could ensure that the stack had a return address where we wanted to go, we'd be set. And that's this code. We decrement the stack to make some space and put on the stack the current instruction pointer. In fact, our previous code just blew away the old instruction pointer. It's like, I don't care where you were in an alarm test, I'm going to forget that. And that's probably not what we want to do. We probably want to remember. So where will we remember? We'll remember by putting it on the stack. So that when alarm handler runs and then returns, it'll go back to where it was.
So where was it returning? Those 2 lines?
Oh, where it happened to return was what happened to be on the stack. And what happened to be on the stack?
The pointers are beginning of main.
Where's the beginning of main? 0. So not unlikely, things are often 0. So there happened to be a 0 on the stack. So that's why it went back to the beginning. If there happened to be FFFFFFF, what would have happened? Lots of Fs, like 8 Fs. It would PageFault because it would be up in kernel space. Yeah. Does that make sense? Okay, just one more thing. We have a problem here. We have a large security hole. The security hole is, who says ESP is pointing into user space? Can I, in a user program, set my stack pointer to point to kernel space? Yes. As long as I don't actually read from it or write to it, I can set it. It's just a register. So if I set it to point up into kernel space, and then I just wait for a timer to happen. That's what I'm going to do. Just wait. And I blow away now something inside the kernel. So we should be checking for stack pointer within the user address range. Just one last thing, and that is, and then I will let you go. Periodic. Is periodic allowed to modify registers? In general, can functions modify registers? Sure. But there's some set of them that they have to restore if they modify them, right? So these are the callee restored registers, or callee saved registers. Are there other registers that it's allowed to blow away? Yeah, there are scratch registers that if the callee wants them saved, the callee will save them. Well, alarm test, the main, has no idea even periodic is going to be running between 2 instructions. So it might save something in EAX. The timer will call periodic. Periodic could overwrite EAX. As far as it's concerned, it's a scratch register, and then it returns EAX has changed. So we need to do something. So we have to do something about caller saved registers. And basically, we need to save them and restore them. But who the we is here is a little unclear. Okay? It'd be a lot of work to say, hey, anytime you set an alarm handler, it's got to be compiled in such a way that it saves and restores all the registers. So instead, it's the kernel's job. So the kernel's going to need to, before periodic is called, save a bunch of registers. But that can't be kernel code. It has to be user code to do that. And when periodic finishes, restore those registers. So when periodic returns, it shouldn't return to where we got interrupted. It should return to a little utility routine that will restore registers that will then go back there.